Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Electrical Transport through Nanoparticle and its growth mechanism from the paper Physics at Nanoscale. So the learning objectives of this module are: first, we will discuss the electrical transport through a nanoparticle. Second, we will be discussing the nanoparticle which is positioned between the source and the drain. Next, we will discuss about the electrostatics, that is the capacitive divider model of the potential. Lastly, the growth mechanism of nanoparticles will be discussed. So students, let us start with a brief introduction about the module. In this module, we will study the current transport through a quantum dot or a nanoparticle between two metallic contacts. So first we have to find out the current voltage characteristics of two terminal devices. So then for three terminal device, a third electrode which is used to impedantly control the electric field on the nanoparticle can be applied to study the current voltage characteristics in three terminal single nanoparticle based devices. So there are different methods for preparing the colloidal nanoparticles, and they can be divided into two categories depending on the nature of the solvent and temperature of the growth. Nanoparticles prepared by wet chemistry uses polar solvents such as water or methanol at low temperature. On the other hand, organometallic synthesis uses non-polar solvents such as trioxyethyl phosphine oxide TOPO as relatively higher temperature. So, students, within each category, there are several variations on the use of precursors, solvents, and special additives as well as temperature and pressures. Out of these methods, organometallic routes generally produces better quality nanoparticles characterized with narrow photoluminescence emission peaks. So in wet chemistry routes, the synthesis temperature is limited by the boiling point of the solvent, typically less than 100 degrees Celsius. So the relatively low growth temperatures produces nanoparticles with higher defect density, resulting in poor optical properties and wider particle size distributions. So the most popular aqueous method is arrested precipitation, which has been used to synthesize a wide range of semiconductor nanoparticles such as cadmium sulfide, cadmium selenide, cadmium telluride, and mercury telluride. For example, in this method, cadmium perchlorate is dissolved in water and hydrogen selenide gas is passed through the solution, and then double replacement reaction, it yields cadmium selenide nanoparticles in the solution. After that, to make the solution alkaline, NaOH is added, and additives such as phosphates, amines and thiols, they are added to protect the nanoparticles. So for better crystallinity and lower density of states, solvothermal processes in which pressure vessels are used to elevate the reaction temperature for better crystallinity. So whereas in a non-polar variation of the solvothermal processes, the dode cannithol capping ligand, that is cadmium stearate and selenium metal, they are combined and heated under the pressure in tetraline, which converts to naphthalene, producing the necessary hydrogen selenide precursor and the resulting cadmium selenide nanoparticles suspended in toluene and other non-polar solvents. So using this method, nanoparticles as low as 2 to 3 nanometers in diameter can be obtained. So now let us start with the module based on the quantum capacitance, that is when there is no applied bias. The Fermi energy must be constant in the metal and the nanoparticle, and charge starts flowing either from the nanoparticle to the metal contact or from the metal to the nanoparticle as bias is applied between the metal contact and nanoparticle. Now it is possible that only a fractional amount of charge is transferred depending on the strength of coupling between the contact and nanoparticle. So let us assume that a fractional quantity delta n electrons are transferred from the contact to the nanoparticle, that is a wave function of the transferred electron. It will be represented by a mixed state including both the contact and the nanoparticle. So hence some part of the electron still stays with the contact. However, when delta n is plus 1 or minus 1, the LUMO or HOMO would be half full respectively, and the Fermi energy would be in the LUMO or HOMO respectively. The transfer of charge establishes the equilibrium and reduces the number of electrons that are transferred after contact is made between the contact and a nanoparticle. The transfer of electrons from the contact to a nanoparticle leaves a net positive charge on the contact and a net negative charge on the molecule, and charging at the interface changes the potential of the nanoparticle relative to the contact. In this scenario, the contact and the nanoparticle can be considered as the electrostatic capacitor, which is represented by CES, which is different from quantum capacitance discussed before. So as shown in this figure, when charge is transferred at the interface, the capacitor is charged, a voltage is established, and the nanoparticle changes potential, which is known as charging energy, and is responsible for a shift in the vacuum energy. So we can write CES equal to Q by V, where V is the voltage across the capacitor. So the change in potential due to transfer of charge by an amount delta n is UC equal to Q square by CES multiplied by delta n. So in the B figure, when a charge is transferred, this electrostatic capacitance determines the change in electrostatic potential and hence the shift in vacuum energy. The charging energy can be very high due to very high electrostatic capacitance. In the case of measurement of current transport through a single nanoparticle, the spacing between the contact and a nanoparticle could be very small, that is approximately 1 nanometer. So the charging energy can be more than 1 volt per electron. So by incorporating the contribution from quantum and electrostatic capacitances, as shown in this figure, the Fermi energy of the nanoparticle contact EF can be related to the Fermi energy of neutral nanoparticle EF naught, and it is given by EF equal to delta N by G as a function of EF plus Q square by CES multiplied by delta N plus EF naught. So this figure shows the changes in the energy level alignment when charge is transferred from the metal to the nanoparticle. Charging of the nanoparticle corresponds to applying a voltage across the interfacial capacitor, thereby changing the potential of the nanoparticle, leading to the shift of the vacuum level's nanoparticle's location, shifting all the nanoparticle energy levels along with it. In addition, the transferred charge fills some previous empty state in the nanoparticle. Both the effects changes the Fermi energy in the molecule. So this figure shows a small signal model for the metal nanoparticle junction, including the effects of charging. To calculate CES, the electrostatic capacitor of spherical nanoparticles of radius capital R, the potential at a point R from the center of the sphere is V equal to Q by 4 pi epsilon R, where the small r is greater than capital R. Epsilon is the dielectric constant of nanoparticle, and Q is the net charge on the nanoparticle sphere, and the potential of the sphere is V is equal to Q by 4 pi epsilon capital R, and the capacitance can be given by CES equal to Q by V equal to 4 pi epsilon capital R. So hence, in the case of nanoparticle, capacitance scales with the radius of nanoparticle. For example, the capacitance of a nanoparticle with the radius r equal to 1 nanometer is approximately CES equal to 10 to the power minus 19 farad, and charging energy is then UC equal to 1.6 electron volt per charge. Nanoparticle positioned between the source and drain electrodes. When a nanoparticle is placed between two electrodes, that is source and drain, to determine the current through the nanoparticle, the potential profile for an arbitrary distribution of charges has to be calculated. So under the approximation that the electric field between two contacts is uniform, the source and drain contacts can be modeled as a parallel plate capacitor with the area capital A, which is the cross-sectional area of each contact, and D is the separation between the two contacts. So this approximation is valid if capital A is very much greater than D, the source and the drain capacitances at a distance Z from the source are given by CSZ equal to epsilon A by Z, CDZ equal to epsilon A by D minus Z. So the potential can be shown vary as well linearly as expected for the uniform electric field. So UZ equal to minus Q VDS multiplied by 1 by CSZ divided by 1 by CDZ plus 1 by CSZ equal to minus Q VDS Z by D. This figure shows that a uniform electric field between the source and the drain metal contacts yields a linearly varying potential. Nanoparticle with two metallic contacts as shown in this figure. So at equilibrium, that is mu1 equal to EF equal to mu2, no current flows through the nanoparticle. So when a potential is applied between the source and the drain contacts, Fermi level of one contact will be shifted to the other. Fermi level of one contact will be shifted with respect to the other, so that mu d minus mu s equal to minus q VDS. So there are two effects on the nanoparticle. First is the electrostatic effect. The energy levels within the nanoparticle will move up or down relative to the contacts. Second is the charging effect. That is, as the nanoparticle is out of equilibrium, a current will flow, resulting in the change in the charge in nanoparticle, and the amount of charge will increase if current flows through the LUMO or decrease if current flows through the HOMO. Electrostatics, the capacitive divider model of potential. So in this model, contact nanoparticle contact device can be modeled by a nanoparticle linked to the source and drain contacts by two capacitors CS and CD respectively. So if the nanoparticle is placed at the middle of the two contacts, then CS is proportional to CD. Now if the nanoparticle is near to the source, as shown in this figure B, but far from the drain, in other words, if nanoparticle strongly couples to the source compared to the drain, CS is very much greater than CD and vice versa. So, as shown in this figure, the figure A shows the symmetric contact and figure B shows the asymmetric contact. The voltage in the center of the nanoparticle is determined by the voltage division factor eta. It can be obtained from a voltage divider constructed from the capacitors. The applied voltage V shifts the chemical potentials of both the source and drain contacts. That is, EF is equal to minus 1 by CS divided by 1 by CD plus 1 by CS multiplied by Q VDS plus mu s. So if the Fermi energy of the nanoparticle at equilibrium is taken as a reference, that is EF equal to 0, mu s equal to plus CD by CS plus CD, multiplied by QVDS. Mu D is equal to minus CS by CS plus CD multiplied by QVDS. So we can define a voltage division factor eta which provides the fraction of the applied bias that is dropped between the nanoparticle and the source contact. So eta is given by CD by CS plus CD. So the voltage division factor eta determines whether conduction occurs through the HOMO or the LUMO. If eta equal to 0 as shown in this figure, then the energy levels in nanoparticle are fixed with respect to the source contact, and as the potential of the drain is increased or decreased with respect to the source, conduction occurs through the HOMO or LUMO respectively. Hence, the current voltage characteristics of this device will exhibit a gap around the zero bias that corresponds to the HOMO-LUMO gap of nanoparticle. So students, as you can see in this figure, that the conduction always occurs through the HOMO when the applied bias is positive, and when the applied bias is negative, the conduction occurs through LUMO. Now consider the case if eta equal to 0.5 as shown in this figure, then irrespective of whether the bias is positive or negative, current always flows through the energy level closest to the Fermi energy, and the gap around the zero bias is more than the HOMO-LUMO gap. So here this is the HOMO irrespective of the applied bias. So the quantum capacitance, the expression for it is given by n equal to integral minus infinity to plus infinity over GE multiplied by FEEF multiplied by DE equal to integral minus infinity to EF over GE DE, where delta EF equal to delta N divided by GEF multiplied by delta EF equal to Q square by CQ multiplied by delta N, where CQ equal to Q square multiplied by GEF. Now delta G equal to N multiplied by mu C minus mu S plus 4 pi r square sigma. So the chemical potential of the system when atoms are in the solution is less than that of the atoms in a crystal, and the minimum of the free energy is obtained when all the atoms are unbound. So no stable crystals are formed. However, we are interested in the opposite case, with the chemical potential of atoms in the solution being more than that of the bound atoms. So the first term becomes negative, resulting in the free energy being a maximum for a certain critical radius RC at which a nucleation barrier is imposed. In the case of spherical nanoparticles, we neglect any variation of the surface tension sigma, that is nanoparticles without facets. In this case, the number of atoms small n in the previously discussed equation can be expressed in terms of the radius small r of the nanoparticle, density of atoms in the nanoparticle ds in nanoparticle, and here in this case delta G equal to 4 pi d3 by 3 multiplied by r cube multiplied by mu c minus mu s plus 4 pi r square sigma. So the chemical potential of the system when atoms are in the solution is less than that of the atoms in a crystal, and the minimum of the free energy is obtained when all the atoms are unbound. So no stable crystals are formed. However, we are interested in the opposite case, with the chemical potential of atoms in the solution being more than that of bound atoms. So the first term becomes negative, resulting in the free energy being a maximum for a certain critical radius Rc at which nucleation barrier is imposed, as shown in this figure. In the case of small nuclei, the surface energy term dominates the free energy, whereas nanoparticle with the radius larger than Rc, the growth is driven by the gain in a chemical potential, and the height of the nucleation barrier controls the rate at which the crystals nucleate. So as shown in this above figure, that first the nucleation occurs at higher temperature, and then at temperature 180 degree around, then the growth of the nanoparticle occurs. So let us now discuss the growth of nanoparticles. Growth of nanoparticle is actually the process of the deposition of monomers onto the growing nanoparticle. It happens in two steps. First, the monomers have to be transported towards the surface of the nanoparticle, and in the second process they have to react with the nanoparticle surface. The first process is controlled by diffusion, and thus the rate of the first process is determined by the diffusion constant d, whereas the speed of the second process is dominated by the rate of reaction between free monomers and the nanoparticle surface. So dr by dt equal to n divided by 4 pi r square dm. So j as a function of x greater than r equal to 4 pi x square d multiplied by dc by dx. So dj by dx for x greater than r equal to 4 pi d multiplied by 2x multiplied by dc by dx plus x square d square c by dx square equal to 0. Now j is equal to 4 pi dr multiplied by cb minus ci. So finally, with this result, the growth rate of a crystal becomes dr by dt equal to d by r dm multiplied by cb minus ci. To this point, an infinite stability of the nanoparticles is assumed, but this assumption is challenged by Gibbs-Thomson effect, which introduces a competing effect to the growth. So as the size of the nanoparticles reduces, their vapor pressure increases. So experimentally also this effect is seen in the lower melting temperature of nanoparticles as compared to bulk. So with the help of Gibbs-Thomson equation, the vapor pressure of a crystal of radius r can be calculated. So through the general gas equation, these vapor pressures can be expressed as the concentrations of monomers in the vicinity of the surface and is given by Ci equal to C infinity multiplied by exponential 2 sigma by r dm kt approximately equal to C infinity multiplied by 1 plus 2 sigma by r dm kt. So in this equation, C infinity is the vapor pressure of a flat surface, sigma is the surface tension. The general dependence of the growth rate on the radius of the crystal is illustrated in this figure. It is interesting to note that the presence of a maximum at a radius of 2r star. If all the crystals present in the solution having a radius larger than this value, the smallest crystals grow fast and therefore the size distribution becomes narrower over the time. So the value of R star depends mainly on the overall concentration of free monomers, but also on the reaction temperature and on the surface tension sigma. So during the run of the reaction, the concentration of monomers decreases and the critical size shifts to the higher values. If the critical size is sufficiently small, the system is said to be in the narrowing or size focusing regime. So during the run of the synthesis, the critical size increases, and as soon as the size of the maximal growth rate 2r star has reached a value situated in the lower end of the size distribution of the nanocrystals. So the system enters in the broadening regime. Ultimately, when R star is larger than the radius of the smallest nanocrystals present, the system enters into the Oswald ripening regime, which is characterized by a large broadening of the size distribution and, more importantly, a decrease of total concentration of the nanoparticles. In the case of fluorescent nanocrystals, the width of the fluorescence spectrum is a good indicator for the quality of the size distribution. So the samples of cadmium selenide or cadmium telluride nanocrystals generally have a band line width of 30 nanometers or less, which in this case corresponds to 100 MeV. So in this figure, it shows an example for the focusing of the size distribution is displayed. So in this example, the synthesis was carried out under conditions that favors size focusing. The nanocrystals were synthesized at a very high temperature, which reduces the nucleation event to a very short time span. Also, the concentration of monomers was sufficiently high to prevent the system to enter into the broadening regime. So students, let us summarize what we have learnt in this module. First, the detailed discussion of electrical transport through nanoparticles has been done. Second, the nanoparticles' position between source and drain has been discussed. Third, the capacitive divider model of the potential in electrostatics has been discussed. Lastly, the chemical potential of the system when atoms are in the solution is less than that of the atom in a crystal, and the minimum of the free energy is obtained when all the atoms are unbound, so no stable crystals are formed. Next, we also discussed about the growth of nanoparticles, which is actually the process of deposition of monomers onto the growing nanoparticle, which happens in two steps. First, the monomers have to be arranged, and in the second process, they have to react with the nanoparticle surface. Next, we discussed that if all the crystals present in the solution have a radius greater than the 2r, the smallest crystals grow fastest, and therefore the size distribution becomes narrower over the time. Thank you.